Hello students, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 22 on instruction sets of 8085 microprocessor. In the previous session students, we have discussed about the internal architecture of 8085 microprocessor and we have seen different control units available in the circuitry of a 8085 microprocessor, and we have also understand what are the operations and what are the functions that are performed by these pins, or we can say control units. In this session we are going to see extensively to the instruction sets of 8085 microprocessor and how the programmings and how the instructions are performed. Okay, so let's start with the initial thing. In the previous session students, we have discussed about the instruction format, that is the opcode and operand. So how we are going to identify whether the instruction is of 1 byte instruction, 2 byte instruction or 3 byte instruction. So what is meant by 1 byte, 2 byte or 3 byte? It is the length of the instruction, that is the number of bytes an instruction occupies in the memory, that is represented as a length of the instruction. So how we are going to identify? There are 2 points that are available with us. You can see that to identify a 2-bit instruction, if a instruction is having a 8-bit value, that is it can either be address or data, and if it is the instruction is having a 8-bit value, it means that it would be a 2-byte instruction. So if for example we can see that if the instruction is MVI A, 09H, so we can see that it is a 8-bit instruction, that is, or we can say it is a 1 byte of it is a 8-bit value, or we can say a 1 byte of value. If it is consisting this amount that is 8-bit value, it means it would be a 2 byte instruction. Why we are saying it is a 2 byte? Because in memory, if we are representing this instruction in the memory, suppose for MVI the mnemonics is XX and we have stored this in 2000H. Okay, so this is the memory address. So in the second byte, that is in the second memory address, this 09 would be stored. Okay, so this would be 2001H. That's why it is known as a 2 byte instruction. Okay. Now the second point is for the 3 byte instruction. So for 3 byte instruction, if the instruction is having a 16-bit value like LDA 1600H. Okay, so suppose we are having a value in such a way, that is we are having a 16-bit value like this. We have a 16-bit value with us, or we can say a 2 byte value. Then we would say that it is occupying a 3 byte memory. How we can say it is occupying a 3 byte of memory? Because suppose we are representing in this instruction in the memory. So suppose this instruction is on the memory address 3000H. Okay, so the mnemonics for LDA, suppose it is YY, so it would be occupied here. The opcode would be occupied here on the 3001 memory address. The lower bit data, that is 1600. In the 1600, what is the lower bit data? That is 00 would be occupied, and at the higher memory address, that is 3002H, the higher bit data or higher bit address would be stored. That's why we are saying that it is occupying a 3 byte of memory. So you can see that how the 2 bytes and 3 bytes are represented, and all the instructions except these instructions would be a 1 byte instruction. Okay, so there is no need to write for 1 byte. All the instructions which is not having any 8-bit value or a 16-bit value in this instruction, that instruction would be known as a 1 byte instruction. Okay, so if you want to write, you can write the rest all instructions. So I hope you have understood what you mean by the length of the instruction, that is the number of bytes an instruction occupies in the memory, and how we are going to identify a 2 byte instruction, a 3 byte instruction, as well as a 1 byte instruction. Okay, so let's move to a memory rule. So what is meant by the memory rule to us? So suppose we should understand that in all memory related operations, the data which is present in lower byte, okay, or lower register is transferred to lower address location, and the higher byte to an higher address location. So it is very important to understand that suppose there is a BC register that is available with us, okay, which is having a value of 2000 H inside it. Okay, here C is represented as a lower byte and B would be represented as a higher byte. So suppose this data is going to be transferred in the memory. Okay, this would be the memory. Suppose this address is say 3000 H, and this address is known as 3001 H. Okay, so the lower byte data would be transferred. Suppose this data is going to be transferred in the memory, it means that the lower byte data would be transferred at the lower address, and the higher byte data would be transferred to the higher address. Similarly, it would be the reverse case, that is, its inverse is also possible, is also true, that is, the lower address data would be transferred to the lower byte, and higher address data would be transferred to higher byte. This is known as the memory rule. So the next point is memory representation of a program. How we are going to represent how we are going to represent a program inside the memory. So to understand it, we are taking one example, that is at 6000 H memory address we have a signal that is move B, C. Okay, at 6001 H we are having MVI A, 60H, and at 6003 H we are having the instruction LXI H, 5432H. Okay, how we have written this? Because we know that it would be a 1 byte instruction, it would be a 2 byte instruction, and it would be a 3 byte instruction, because there is no 8 bit or 16 bit data available. That's why it is a 1 byte instruction. There is a 8 bit value which is available, that is why it is a 2 byte instruction, and there is a 16 bit value available here. That's why it is a 3 byte instruction. Okay, now we are going to represent this program in the memory. Okay, so we can see that this program is started from 6000 H. Okay, so in 6000 H memory address, first of all the mnemonic of this move would be stored. So we can assume that move's mnemonic is XX, it is YY, and its is ZZ. So first XX would be stored. Now as there is no data to be stored again, and it is representing a 1 byte instruction, that is the memory occupied in the storage would be only 1 byte, that is occupied by its mnemonic. Okay, now next on 6001 H the mnemonics for MVI would be stored, and at 6002 the data that is present, which is 60, is going to be stored. Similarly, this represents that this instruction is of 2 bytes. Now for 6003, we can see that we have marked 6003 correctly because the above instruction is occupying 2 bytes of data. Therefore, from 6003, the next instruction would be implemented and its mnemonic is ZZ. Okay. Now on 6004H. Now 6004H, the lower address or at lower address, lower byte data would be present. So we can write 32 here. And at 6005H, higher bit data would be present, that is 54. So we can see that it is occupying 3 bytes of memory, it is occupying 2 bytes of memory, and it is occupying 1 byte of memory. So this represents the memory representation of the program. So with the help of memory representation, when the microprocessor would access this memory, we are able to solve or to execute this program. So don't worry about these instructions, students. When we are going to see what are the meaning of these instructions, you would be able to understand that. Okay, now one point is, that is note, the number of machine cycles for an instruction are not always equal to the length of the instruction. So students, what is meant by the machine cycles? We have studied the basic operations of the microprocessor, that is fetch, memory read, memory write, IO read and IO write. So to implement these operations, the time period or the cycles required or to access the memory or to access the memory or the output input devices is known as machine cycle. Okay. So it is not always equal to the length of the instruction. So when we are going to study these instructions, you would be able to see that the machine cycle involved in this instruction is fetch. The machine cycle involves are fetch plus read, and for this there would be fetch plus read plus read. Okay, so these are the machine cycles involved, but here we can see that the number of bytes is equal to the number of machine cycles. Here 2 bytes, 2 machine cycles, 3 bytes, 3 machine cycles, and this note is saying that it is not always equal to the length of the instruction, but from the bytes only we can assume or we can understand what are the minimum machine cycles that going to be present, because there are some instructions for which the bytes is less than the machine cycles. Suppose there would be an instruction which is having a 2 byte of data, but the machine cycles would be performed higher. So from the bytes, from the knowledge of bytes, we would be able to understand that minimum this amount of machine cycles would be present in this instruction. Okay, so from seeing the 2 bytes, we would be able to comment that at least 2 machine cycles would definitely be available for this instruction, and there can be more than that. But for this specific instruction, that is MVI, there would be only 2 machine cycles. Whenever there would be higher, we would be going to discuss that. Okay, and the second note point is, after decoding an opcode, the processor can understood. We have discussed this point in the previous session also, that after the microprocessor decodes a opcode, it would be able to understand what is the length of the instruction, students, and what are the number of machine cycles that are involved in execution. So with the length of the instruction, it would be able to understand what are the values it has to access from the memory, and with the help of machine cycles, with the knowledge of machine cycles, it can perform the operations on the content of the memory. Suppose the machine cycle involved are fetch plus read plus read. It means that first it will be going to fetch the opcode from the memory, then it would be going to read the content from the memory, and then it would read the content from the memory, because there are 2 read operations that are available in the instruction. Okay, so these points are very important. These are some of the basics regarding the instruction set, and it would be very helpful to understand the instructions properly. So you can write these points. Next, we are going to see what are the addressing modes in the 8085 microprocessor. So I hope you have written all the points. Now we are going to see what are the addressing modes present in 8085 microprocessor. So what an addressing modes represent? It indicates how data is accessed for an instruction, how the data is accessed for an instruction. So there are 5 addressing modes that are available. First is immediate addressing mode, that is the data is present in the instruction only. So to take an example, we have an instruction with us, that is MVI B,06H. So we can see that the data is present in the instruction only. That's why it is known as immediate addressing mode, because the data is immediately present in the in the instruction. Second is direct addressing mode, in which the address of the data is present in the instruction. For example, let us take an example, that is LDA 8000H. So what this instruction means, that the data which is present at this address inside the memory would be transferred to the accumulator. So suppose this is 8000H and the data present is 15H. Okay, so this data would be transferred to the accumulator, which is present inside the microprocessor. So we can see that here the address is directly present, therefore it is known as direct addressing mode. In the third, that is indirect addressing mode, in this mode the address of data is present as a content of another register pair. So what it means, that the data is present as content of another register pair. For example, we take an instruction LDAX B. Here what it means, that here X represents indirect. This is the symbol for indirect addressing mode. It means that suppose in BC register pair there is a data present, that is 8000. Okay, so here we are representing the address of the data as a content of this register pair. So in the memory, when we see this 8000H, and whatever data is present would be transferred to the accumulator. So instead of giving this 8000H directly in the instruction, what we are going to do, we are going to represent it, or we are going to give the address indirectly by giving a register pair which is containing the address of the required data. So this is known as indirect addressing mode. The fourth mode is the register addressing mode, that is the data is transferred between registers. So how the data would be transferred between registers? It is a simple one. Suppose it is move B, C. So here we can see that the data is transferred between the registers, that is the data present in C register would be transferred to B. So there is not present any address or any data. It is just the registers available in the instruction. That's why it is known as an registered addressing mode. The fifth and the last addressing mode is implicit addressing mode, where no operands or the data is present in the instruction. So for example, we can take an halt operation. The operation or the function of this halt operation or halt instruction is to stop the sequence of the program. So with the halt instruction, you can see there is no data or no operand is present. That's why it is known as an implicit addressing mode. So there are 5 addressing modes: immediate addressing mode, direct addressing mode, indirect addressing mode, register addressing mode, and implicit addressing mode. So sometimes there would be questions to just know what would be the addressing mode of the instruction. So you can see that wherever data would be present, it would be an immediate. Where address is present of any data, then it would be direct addressing mode. If the data or the address of the data is represented as an content of any register pair, it means that it would be an indirect addressing mode. If there are only registers available, that would be register addressing mode, and if there is no operand or data present in the instruction, that would be an implicit addressing mode. So these are addressing modes. I hope you have written all the addressing modes. Now we are going to discuss the timing diagram. So timing diagram is important to understand the pictorial representation of the execution of an instruction. So with the help of some various control, timing and status signals, we are able to understand how we are going to represent or construct the timing diagram of any instruction. Okay, so the components which is very important in the timing diagram are T states. So what are T states? It is a one subdivision of the operation performed in one clock period. Okay, and what is machine cycle? We have discussed machine cycle earlier. So to the time period required to access either memory or our input output to perform specific functions, that is fetch. Either it can be an opcode fetch, it can be a memory read, it can be a memory write, it can be IO read, or it can be IO write. So to operate these operations, to perform these operations, the time period which is required to access this memory or the input output would be known as machine cycle. It is also equivalent to the time required to transfer the data byte to memory or output. So this definition would include all the prospects, that is either we are taking the data from memory or input output, or if we are transferring the data into memory and input output, the time period required would be regarded as the machine cycle. So in one machine cycle there can be minimum 3 T states. It would be totally dependent on the instruction, totally depend on the operation that we are performing. So minimum T states possible are 3 and maximum T states possible are 6. And what is an instruction cycle? It is the time required to complete an execution of an instruction. So the total time required to complete an execution of any instruction would be regarded as a instruction cycles. So in instruction cycles, it may be either it may require either one machine cycle only, or it may require maximum 5 machine cycles. So what it means by one machine cycle, that is if a instruction cycle is having only one machine cycle, it means that the whole operation is performed in the opcode fetch, because for every machine cycle, the first for every instruction, the first machine cycle would be opcode fetch. That is, we are fetching the opcode from the memory so that the microprocessor can understand that which operation is going to be performed. So it is very important to first fetch the opcode from the memory so that it can understand the operation that is going to be performed. So this is the quite important points regarding the timing diagram. You can write the basic definitions quickly, then we are going to see the complete timing diagram using one example. So suppose we are taking a timing diagram and let us consider an example with us, which is suppose we are having a memory address 8090H, and at this memory address we have a data we have an instruction MVI C, 90H. Okay, so from this we can understand two things, that is, it is a 2-byte instruction because there is a 8-bit value present inside the instruction. There would be a 2-byte, that is, it would hold a 2-byte of memory inside the storage, and the machine cycles involved would be fetch and read. So why we are saying that this instruction is having a fetch machine cycle and a read machine cycle? So students, it is very important to understand this concept, because in every data transfer instruction it is very necessary to understand how many machine cycles it would going to perform. So with by seeing just the number of bytes, we would be able to understand the minimum machine cycles, but we are not able to understand what are the exact number. Okay, so to understand it, please understand what is the internal functioning that is going to be done when this operation is going to be performed. Okay, so I'm explaining this point here only so that it would be clear in rest of the instructions. Okay, so in microprocessor there would be one, that is instruction register. There would be a register that is a program counter which is controlling the flow of the counter, and suppose the memory address is starting from 00, but we are going to see for 8090H and 8091H. So from the length of the instruction we are able to understand that there would be 2 bytes of memory. So in the first byte the opcode would be stored for this instruction, and in the second byte this 90 data would be stored. Okay, so there would be an interfacing between this, like, okay, so what this instruction means, that this 90 data would be stored in C register. So we are drawing again C register. Okay, so when this program, or when we press the execute button, first of all the program counter would be fed with the program counter Suppose this is a program counter and this is the register. So when the execute button would press, then it would be stored with 8090. Okay, so at 8090 whatever data would be present, it would be entered in this instruction register. So this data would be accessed in this, and this instruction register then would decode this opcode. So after decoding, we would be able to understand what are the length of the instruction and what are the machine cycles involved. So with the help of the length of the instruction that is understood by the microprocessor, we would able to understand that this data belongs to this instruction only. And with the help of the machine cycle, it would able to understand that what operations is going to be performed by this instruction. Okay, now after the decoding, the program counter would move automatically to the next memory address. Now as the microprocessor knows what operation is going to be performed, therefore now the content of this address, that is 8091, would be accessed with the help of the data lines, and it would travel and it would get stored in this register. So with the help of the machine cycles, we are able to understand what operations is going to be performed. So the first machine cycle for every instruction would be a opcode fetch, because with the opcode fetch we would be able to understand what is the type of the instruction and what operation is going to be performed. And from the second machine cycle, that is read, it tells the microprocessor that it would going to read data from the memory, and then it would transfer into the any register. Okay, it can be either memory read or it can be either memory write. If it is W, it means that the data present inside the microprocessor would be transferred to memory. Or it can be more than one read operations and one write operations. So depending on the instruction, we are going to see there. Now to to complete the timing diagram, we can see that the first machine cycle would always be opcode fetch. Okay, so when the ALE signal would be logic high, it means that we know that whenever ALE is equals to 1, it means that all the lines, that is all the address lines from AD0 to AD7 and A8 and A15 works as an address lines. Therefore, so as all the lines are working as an address lines, so this data, that is now the address lines, these are the representation of transmission lines or the buses available for the addresses as well as data. So this would hold the address of the first memory, that is 8090. So here it is higher byte address, so it would hold the 80, and as it is lower byte address, so it would hold 90. So this address is stored in this. So after getting this, it would able to read the content that is available at XX. So in T1, what is the operation that is performed? It would it reads the address. Okay, so in T1 T state, it would read the address. Now after the T1 T state, there is no requirement of the address lines. It is already connected, so it will go low, and in the second T state, the read operation would go low. That is, it would become active. As read signal is become active, therefore the data and ALE is become low. It means now the lower bit address lines would be working as a data lines. So whatever data is present in this address would be latched, that is access would be latched to these lines, and it would transfer to the microprocessor. Okay, so this data is latched, and you can see read bar is also active. For the complete instruction, as there is no write operation, so it would remain always inactive. Okay, this is the inactive nature. Okay, now after reading, and you can see the status also, IO bar, M bar, S0, S1 would be 0, 1, 1. Okay, so in T4 T state, what is going to be performed? As that opcode is latched, so decoding of this opcode would be performed. Okay, so in T4 T state, opcode, the decoding would be performed, and in T3 T state, the what function is going to be performed? In T3 T state, opcode is accessed into IR. Okay, so this data is latched to IR, and then in T4 decoding would be done. So this up to T4 T states, the whole operation is opcode fetch. Now it is going to read the data, that is now again the first T state of every machine cycle would be a address, it would be working as an address state, that is ALE would be again high. It means that all the lines would be working as an address lines, so it would again read 8091H. Now as this is latched with the microprocessor, it would again become low, and as it is become low and the read operation is active, read signal is active, it means that 80 and 87 are working as an data lines. Now the data is transferred, that is the data is 90, so this data would be transferred and it would store in this C register. So you can see that the status signal is represented by 001, because we know that for memory read, IO bar M bar would be 0 and S0 S1 would be 0 1. So this is the timing diagram for this instruction. Okay, so it is very simple. You can able to draw for any signal you want. Okay, so the conclusions that are drawn, you can write the conclusions that are drawn from it is conclusions. What are the conclusions? From the timing diagram, we are able to understand the length of the instruction. What is the length of the instruction? Second is how many machine cycles we are able to predict and what are the functions of the machine cycles. Third is total T states. Total T states. So as the machine cycles was fetch plus read, so for fetch there are 4 T states and for read there is 3 T states. So total would be 7 and total number of instruction cycle is 1. Okay, so this is the conclusion that is drawn from this, and if we want to generalize our T states, we can write as for fetch minimum T state and maximum T states are how many? So for fetch we can see that minimum are 4 and maximum would be 6. So there would be some instructions there in which the T states for fetch operation would be 6. Okay. So for machine cycle, if we want to write, we can see that for machine cycle, for any machine cycle, minimum T states are 3, because we can see that in memory read 3 T states are required and maximum possibilities are 6. Okay. And the instruction, for instruction if we are writing journal view, so minimum T states would be 4, because if there is one machine cycle in an instruction, so it would be having only minimum 4 T states. Okay, because that machine cycle would obviously be opcode fetch and the minimum value of T state is 4 and the maximum T states possible for an instruction is 18. So these are the data for 8085 microprocessor, and this was the timing diagram for any instruction. So this was for understanding point of view. The main point is this block diagram. With the help of this block diagram, we would understand what operations is going to be performed. Okay, so I hope you have written this whole timing diagram, and this point is very important, how the operation is going to be performed. Okay, so this is very important, because for every data or copy instructions that we are going to study next, we would be seeing the complete view so that there would be no misunderstanding or there would be no confusion later on during the revision. Okay, so maybe it would take some time, but we should understand all the concepts clearly. Okay, so this was the instruction operation timing diagram as well as some of the important points regarding the T states. Sometimes direct operation or the question is based on these T states. So it may be asked in T state 1 what is the working. You can write for T2 also. In T2 ALE becomes 0 and AD0 to AD7 is working as a data bus. Okay, and you can see in T2 state only the read signal is available. So these are quite peculiar points, important points regarding T2 state. We have written for T3 also, opcode is accessed to instruction register in this T state, and in T4 decoding of the logic is performed. Okay, so I hope you have written all the points regarding this. Now we are going to start our instructions. So first type of instructions that we are going to discuss would be the data transfer and copy instructions. So the first instruction is MVI R, 8-bit data or address. What is going to be performed? What function is going to be performed with this? The 8-bit data would be transferred to the register. So with the help of example, we are going to see MVI B comma 06H. So which function is going to be performed? It would transfer 06 to B. So by seeing this instruction only, we should be able in a position to comment on the machine cycles, number of bytes and number of T states that is required by this instruction. So number of bytes, we can say that bytes requirement is 2 because there is a 8-bit data present, and with the help of bytes we would be able to know that minimum 2 machine cycles are required. So the first machine cycle would be fetch, okay, it is the compulsory machine cycle, and second machine cycle should be opcode, should be memory read, because this data is present in the memory. So we have to access the memory so that it can be transferred in register which is present in the microprocessor. So the second machine cycle should be a read machine cycle, or specifically we can say memory read. Okay, so number of T states involved would be, for fetch it would be 4, for read it would be 3. So the total T states are 7 T states. Okay. And we should also comment on the signals of read, write and ALE. So we can, from this we can understand how many times read signal would be activated. Read signal would be activated always that time when we are reading some data from the memory. So when we are reading, or when we are doing the opcode fetch operation, we are taking the opcode from the memory, and when we are reading the content, that is 06 from the memory, we are accessing the read signal. So 2 times it would be activated. Similarly, write operation, there is no write operation that is performed on the memory, so there would be no activation of write signal. And what is ALE? Address latch enable. It means that how many times we are accessing the address, or we are taking the address from the memory. That is, when we are reading 2 bytes, that is fetch and read, we are accessing the addresses, so the ALE would be activated 2 times. So these points can be seen from this figure also, that is ALE is accessed 2 times, read signal is activated also 2 times, and write is not activated once in this instruction. Okay, so if you want to understand this system, that is how we are able to comment fetch and read, you can take the help of this structure, that is by drawing the microprocessor and the memory, and with this you can first fill the data. So whatever memory address this is present, first fill the opcode, then fill this data, and try to understand how the program counter would control the flow of this instruction. So first of all, the opcode would be fetched to the instruction register. Okay, so the first machine cycle would be fetch, and the second machine cycle would be read, that is it would be reading 06H from the memory, and it would be transferring it to the B register pair. Okay, now we are going to see move operation. So move operation is, we are transmitting the data from RS register to RD register, that is the source register, to the destination register. But it doesn't mean that the data would be removed from the source register. It means that it is like a copy function, that is the data would be available at source and as well as the destination. Okay, so this is the meaning of this instruction, and now we are going to see what are the number of bytes, or what is the length of the instruction. So as there is no data present, so it would be 1 byte, and with this we can able to understand that how many minimum machine cycles are required. Minimum machine cycles is 1, but for this case the actual number of machine cycles is also one, that is fetch. So we should understand why only in one machine cycle this whole instruction is performed. So we are going to take the help of this structure again. It is very important structure to understand and to solve the problems also. Okay, so suppose we are taking an example like this. So suppose this is an example which is on 6000H memory address. 6000H memory address, we have an instruction move B, C, that is the data present in C register should be transferred to B. So these registers are present in the microprocessor only. This is microprocessor. Okay, this would be the program counter. This would be instruction register, and this would be the interfacing between this. So suppose the opcode is present and this memory address 6000H would be XX. We are assuming the mnemonics for move is XX. Okay, so on accessing when the program counter is fed with 6000, it would access the opcode and it would transfer to instruction register. So after decoding it, the microprocessor would be able to understand what is the instruction that is going to be performed and what are the machine cycles and bytes available for this instruction. Now there is no memory access required again, because no data is accessed from the memory. Data is going to be transferred within the microprocessor, because the data is going to be transferred from C to B. So there is no requirement to access the memory again. Only one access, that is fetch, is required, because we have to access the opcode from the memory. That's why we are using only one machine cycle, that is fetch. Now this data would be transferred here after this instruction is executed and we would get our result. That's why only one fetch is performed. And you would be able to differentiate from this here why read is performed, because we are accessing the data from the memory only. Okay, so this is this operation, and now we can comment on the T state. So the total T states required would be 4. T states are 4, and for this you can also comment on the read, write and ALE signal. So read operation would be only 1, because when we are accessing the data from the memory. Write operation is again 0, and address latch enable would also be 1, because only one time we are accessing this address from the memory. Okay, I hope you have able to understand move RD, RS. Now the third instruction is LXI RP, 16-bit value. So what it means, that is whatever 16-bit value is present in this instruction, it would be transferred to register pair. RP stands for register pair. So where this 16-bit value would be present in the memory. Okay, so to take an example so that it would be clear how we are getting the bytes, machine cycle and T states. Suppose it is stored in 2000H memory address LXI B, 1 2 3 4 1 2 3 4 H. Okay, so this is the memory address in which this is performed. So to construct the memory representation, we are taking the help of again the block diagram like this. This is our microprocessor and this is our memory representation. So at 2000 the opcode would be present. So again we are assuming for LXI mnemonics is XX. Now at 2001 what is present? as it is a 3-byte instruction, so the lower bit data would be present here and the higher bit data would be present in the next byte. Okay, so what is this instruction performing? What is this instruction is doing? It is transferring the 16-bit data which is present in the memory to the register pair. Okay, so the number of bytes we have understood, because we know the shortcut is 3. Okay, now the machine cycles involved is, first we are going to fetch this opcode. So the first machine cycle is always fetch. Now in the second machine cycle, this data is transferred to the BC C register. So one memory read operation is required. Okay, and in the second memory read operation, when this is accessed, this data would be transferred to B. So by this representation, we are able to understand that how many machine cycles are required. So if for the first machine cycle, it would fetch our opcode. In the second machine cycle, it would fetch the data that is transferred to C, and in the in the third machine cycle, which is again memory read, it would transfer this data. And the total T states would be 4 plus 3 plus 3 would be equal to 10. Okay, so I hope you are able to understand this clearly, because in the next instructions, we are not drawing this diagram again and again. We would be understanding orally from the instructions. So I hope you have clearly understand this diagram. If you have any doubt regarding any instruction, you can make this diagram, this block representation, and you would be able to understand why we are getting these machine cycles. Okay. Now we are going to see next instructions, that is move R, M. So what this instruction is going to perform, that the data, this instruction copies the data to register R from the memory location pointed by HL pair, or we can write like this also: whatever content is present in HL register pair, it would be the address, and at that address whatever data is present, it would be transferred to register R. So number of you can see in this instruction, bytes of memory stored would be 1, and machine cycles present would be, first machine cycle would be fetch operation, and the second machine cycle is the read operation, when it will going to read the address which is stored in HL pair. So in this read operation, it would read the data which is stored at the memory address which is pointed by HL register pair. So the total machine cycles are fetch plus read, which gives T states is equals to 4 plus 3, that is 7. Okay, and one more point, which addressing mode it is working as? It is working as an indirect addressing mode, because we can see that there is no direct address present in the instruction, as well as there is no data present. We have indirectly given the address of the data which is going to be transferred to the register. That's why it is known as indirect addressing mode. Similarly, if we see the next instruction, that is move M, R, what it means, that the data which is it copies the data. You can write the whole instruction: copies the data from R to the memory location pointed by HL pair. Okay, so whichever memory location is pointed by HL pair, at that memory location the data present in this register would be transferred. Okay, so similarly here number of bytes would be 1. Machine cycle involved would be fetch plus here would be write, because we are writing the data in the memory. Therefore, we have used the write operation, and the t states available would be 4 plus 3, that is 7. Okay, so these were two operations. Next operation is MVI M, 8-bit data. So what operation is going to be performed? That it would transfer this 8-bit data to the memory location pointed by HL pair. Okay, so you can write 8-bit data is transferred to memory location pointed by HL pair. Okay, so here you can see there is a 8-bit data, so the total bytes occupied in the memory would be 2. What are the machine cycles involved? First would be fetch operation. So the opcode fetch machine cycle is the first machine cycle. Next it would access this 8-bit data. So the next operation would be the read operation. Then whatever data is present here, it would be transferred to that memory location that is present or that is pointed by HL pair. So the next memory the next machine cycle would be then read or would be an write operation, that is the memory write. So the total t states would be involved in this instruction would be 4 plus 3 plus 3, that is 10 t states, and the addressing mode for this instruction would be immediate, because we are immediately providing the data in the instruction only. So the important point is machine cycle. First machine cycle would be opcode fetch, by which we are fetching the opcode of this instruction. In the second cycle we would be fetching or we would be accessing the 8-bit data. Suppose the example is giving like MVI M, 06H. So at suppose it is present at memory address 8000. So if we are available with this 8000, so here would be the opcode, and 8001 the data would be available. Now in the second machine cycle this data would be accessed, and again this data would be transferred to the memory location pointed by HL pair. So suppose in the microprocessor HL pair is pointing at 9000H. So at 900H this data would going to be transferred. Therefore the second machine cycle which we are using is an write operation. Okay, so I hope you have understood these three instructions also. You can write these instructions. Next we are going to see our next set of instructions. Now the next instruction is LDA 16-bit address. So what is going to be done in this instruction? The data which is present in this 16-bit address would be transferred to the accumulator. Okay, so we can write load accumulator with data present in given memory location. Okay, So this is the functioning of this address of this instruction. For example, we are taking LDA 1600H. So with the help of this, we are going to find what are the bytes required. We can see that there would be 3 bytes required because a 16-bit value is present, and machine cycles involved would be first would be the fetch operation. In the second machine cycle, the lower bit data would be read, and in the third machine cycle, the higher bit data, that is 16, is going to be read from the memory, and then the whole data which is present in this 1600H memory location would be read from the memory. So the total machine cycles involved are fetch plus read plus read plus read. So we can see that it is a 3-byte instruction, but the machine cycles involved are fetch plus read plus read. So we can see that the minimum machine cycles would be 3, but it can be more for some instructions. So the total T states available would be 4 plus 3 plus 3 plus 3, that is 16. Okay, so the 9th instruction is store the data of 16-bit address in 16-bit address memory location from accumulator. So whatever data is present in the accumulator would be stored in this 16-bit address. For example, we have STA 1800H. So with this we can see the bytes would be 3. Machine cycles, how many machine cycles are involved? So the first would be the fetch machine cycle. Next, 2 read operations are necessary to read this address, and the last operation would be the write operation, because we are transferring the data from accumulator to the memory. So the last operation would be memory write operation, and total T states would be again, this is 13. So the total T states would be again 13 T states. Okay, so the next signal is LDAX RP. So this is the indirect operation. This is indirect operation, that is it would load the accumulator with data which is pointed by the content of this register pair. So whatever data which is present in this register pair, at that memory location, whatever content is present would be transferred to the accumulator. Similarly, this would be the store, that is it would be the opposite operation for LDAX. Okay, so the cycles or the machine cycles involved would be, as we can see, it is a 1-byte operation, and the machine cycles are fetch to fetch the opcode, and second would be the read, so that it can read the content from the memory, that is the memory address can be read from the memory. So fetch plus read here, and here would be fetch plus write, and total T states would be 7 for both. So these are the instructions that are LDA 16-bit address, STA 16-bit address, and LDAX RP and STAX RP. Okay, now we are going to see push and pop operations. So push and pop operations are related to the stack, because with the help of push operation, what we are going to do, whatever data is present in this register pair would be transferred to the stack. That is, suppose we are pushing push B. So whatever data is present in BC register pair would be transferred to the stack point, to the stack. Okay, so suppose stack is filled up to 3000 H, and we know that the up to and below it would already be filled. So at 2FFFH address, and what would be the data at 2FFEH? So as it is a lower bit address, so lower bit data would be stored, and at higher bit, at higher address, higher bit data would be stored. So with the help of push operation, what is we are doing, the higher bit data would be stored to SP minus 1 memory location. So as SP is 3000, so at SP minus 1, that is 2FFF60 would be stored, and the content of RL, that is lower bit register, would be stored in the memory location SP minus 2. And the stack pointer, the content of the stack pointer, when we studied the stack pointer, the content of the stack pointer which is pointing at the top of stack would change from SP to SP minus 2. Okay, this is the push operation. The just opposite is the pop operation. In the pop operation, whatever data is present in this stack, which is present inside the memory only, would be transferred to the register pair. So SP minus 1, at SP minus 1 memory location, the data would be transferred to RL. From SP the data would be transferred to RL, because we are transferring from stack only, and whatever data present at SP minus 1 would be transferred to RH. Okay, and the stack pointer, the content of the stack pointer which is pointing, this would be outside, you can write, this would be SP minus 2. Okay, this would be SP minus 2. Now the content of the SP would change from SP plus 2 to SP. So to understand using the example, suppose we are taking an example pop B, and we are showing a stack with 3000 H, 3001 H, and 3002 H. Here 1, 2, 3, 4, and some data which is present. So the stack pointer is pointing at the top of stack. So initially SP is 3000. Now the data, when this operation would be executed, the data present at 3000 would be transferred to lower bit register, that is here 12 would be transferred, and at higher memory address the data would be transferred to the higher bit register using the memory rule. Okay, and this is SP plus 1 and this is SP plus 2. So this is SP plus 1. So SP data would be transferred to RL. SP SP plus 1 data would be transferred to RH, and as these two data are popped out using LIFO technology, now the new stack pointer or the content of the stack pointer is changed from SP to SP plus 2. Okay, so these were the two push and pop operations performed on the stack. I hope you have understood. You can write these points. Next we are going to see some more operations. Okay, Now the next operation that we are going to see is in 8-bit port address. What is it's doing? That is, whatever data is present in input port address would be transferred to the accumulator. So it is very important that whatever content would be present in the input device would be first transferred to the accumulator only. So you can see number of bytes involved would be 2 bytes, because if we take the example IN83H, so there is a 8-bit content, so therefore the length of the instruction is 2 bytes, and the machine cycles performed would be, first would be fetch, second would be the access of this data, that is read, and then at this port address whatever data is present would be transferred to accumulator. So the next operation is also read operation. Okay, so the total machine cycles are 3, and the t states present would be 4 plus 3 plus 3, that is 10 t states. Okay, so for there can be 2 types of mapping. Okay, for input in 8-bit port address, it can be IO mapped IO, or it can be memory mapped IO. Okay, so these 2 operations would be understood more clearly in the interfacing part, but we can mention here that we can transfer data from directly input device, or we can take this data present in the memory, and we can hold this memory address in the memory, and we can access the data from that also. So it would be memory IO map IO and memory map IO. Similarly, for out 8-bit port address, the opposite or the inverse operation of in instruction would be performed, that is, the data present in accumulator would be transferred to the port address which is given in the instruction. Okay, so it would also be a 2-byte operation. First operation would be fetch, second machine cycle would be read, so that it can read this 8-bit port address, and third operation would be IO write, because it is writing here. It is the third operation is specifically IO read, that is, we are reading the data from the input device. Here we are writing the data to the output device. That's why the last operation is IO write, and the total t states are again 10 t states. So I hope you have understood in and out operations also.